So my goal is to try to make some link between some Motivic and topological Milnor fiber or fibration. So that's some object we have already encountered in this conference. And one way to produce such a link will be via logarithmic geometry that we also encounter. So I hope you remember all the definition, notation. I will use them freely and randomly probably during the talk. And that's a joint work with Jean-Baptiste Campesato and Madame Parusinski, which is there. So let me try to, as you know everything about all of this, to go directly to the point somehow of the talk. So let's say that we take some algebraic variety over C and take some regular function on it. Then Arthur defines the so-called Motivic Milnor fiber associated to such a function. So he produced some sum of classes in a Grothending ring of varieties. So maybe it's not exactly the same notation. So that is some class of some complex variety in the Grothending ring of varieties. And he mentioned that this object that I will denote this by S is related to the topological Milnor fibration in the sense, so let me denote this by F, so cell local, so related to the function f and at some point x0 in the zero set of f. And so there are some relations between these two objects. If you compute, let's say, any additive and multiplicative invariant on both objects, you obtain the same thing. So, for example, if you consider the Euler characteristic of them, then you obtain the same number. Or of course, you have more complicated additive invariant like Hodge-Döding polynomials and other examples. So that's the Motivic Milnor fiber, and let's say that's the topological one. Some algebraic variety. Of course, I will come back to this later. Yes, I just want really to come to the point and then explain a bit more the object there. So my goal in the talk is somehow to give some sense, some heuristic at least, to these signs which appear there. This is some alternating sum. You can imagine some rules with intersetting varieties or this kind of thing to produce such a sum. And yes, I want to try to give some explanation for why do we need this sign there. And to do this, I will pass via logarithmic geometry. So that's really say a first introduction for the talk. So let me maybe define a bit more precisely the object there. So I don't know to which extent I should be very precise on the topological Milnor fiber, but at least maybe do a drawing to give some idea of what it is, even if it appears in a lot of talks previously. So let's say that we have the zero set of our function, which is something like this. We want to consider this, so that's let's say a singular point or a point in the zero set, possibly singular. we are going to consider this in some ball. Around x0, and so Milnor fibration theorem say that, so let's say that this goes to C. So you have 0 here, and if we restrict to some small enough disk around C, let me use maybe some colors. Let's say that that's, let's say, inside a disk with some radius, say delta. You remove the origin in the disk, then you have some kind of tube here above this point, this disk. Also, Milnor theorem say that when we restrict to this tube, but remove the singular fiber, then this is a fibration. So let's say that some ball with radius r. And so we have a fibration from this ball intersected with the inverse image of this disk. I'm going to the disk, so for a small enough value on small r on delta. So probably in this setting, that's maybe rather a lay approach of the fibration. So that's something like this. And Milnor original proof, the fibration was a bit different. Even equivalent, so we consider not the full ball but just the sphere. Then you remove the zero set, so you remove the point there, and you go to S1 by taking the argument of a point. So F. About the modulus. So this is a fibration. We have a fiber, so one particular fiber somewhere. And this is a invariant of the singularity, which is a rich invariant of this singularity. We can do a lot of things with that, but Patrick explained this already. So let me skip now to the, so this was a topological approach. And so this F, yes, is this object here. So let me give some word about the definition of this object now. So as you see here, we need to choose small r and delta small enough, so you have some choices to do, but they're not intrinsic. The Motivic approach produces an object which is intrinsic. And moreover, this is, of course, a topological object or differentiable object. We can put a differentiable structure there, but certainly not algebraic, as you cut with a ball. So there is an algebraic approach to this. So that's the Motivic approach. So we already encountered the. So let me maybe say that was by Denef and Loser some time ago. I think something like this for the paper. So this object will live in the Gotelling ring of complex varieties. So we encounter several times also this ring. Let's just say that some, say, universal ring so generated by classes of algebraic variety over C. So this bracket will be for these classes. And you have some relation. So additivity relations. So if you have a close immersion, then the class of the big variety is the class of the small, plus the class of the complement. There is a special class in there given by the affine line. And so we need to invert this class in this ring to consider this Motivic Milnor fiber. So let me define M to be this ring with L inverted. So I mentioned universal. So the sense of universal there is that if you have a, yes, maybe I have to say two things. First, this gives maybe some relation for additivity. Of course, you have product, so this gives a ring structure. And universal in the sense that if you have any additive invariant on a complex algebraic variety, like a Lerche characteristic, that gives you a ring morphism. So for instance, is blue okay? I don't know. A Lerche characteristic gives you a morphism to the integer, and if you have any other such additive morphism, for instance, Hodge-Döhling polynomial, this gives you an additive invariant from this ring to a polynomial ring. So this is universal. And so what is the Motivic Milnor fiber in this ring? Well, so we can define some zeta function associated to F. So to such a function, you can associate some arc spaces. So let me write this like, well, some measures of some arc spaces associated to the function around the point. Sorry, this is English. Something like this, maybe. So some arc spaces, and this is should be a series in T. So this zeta function is some generating series. The coefficients are some measure in this Gotelling ring with the class of the affine line inverted. And well, there is some way to define these arc spaces. Arthur says some word about it. I will not need the definition, so I will not specify it here. What is of interest for me is that this generating series is actually a rational function, and we have an expression of this rational function in terms of a resolution of the singularities. So, let me continue maybe here for the moment. maybe not here. Okay, let me try to write it down there at the moment. So we have, well, let's go here, sorry. So this zeta function has a rational expression in terms of a resolution of the singularities. So again, I will not define maybe all the terms appearing here. I will just say some word about it. So here you have some index sets related to the resolution of the singularity you have chosen for your function. So you have, say, the exceptional divisor. That will be the union of some divisors. So here you pick some subset inside this union of divisors. Then you have canonical certification of this union by for a subset J. You may consider the intersection of all divisors in this subset, and you remove all other divisors. So that produces you such a certification. Yes, so if you have several, let's say, two divisors, then you have this, for example. So, and above all these strata, you may define some bundles, some normal bundles, which give some of this set. And here you have a rational expression with some numerical data here coming from the resolution. Again, that's not so important at the moment here. So we can give some sense of the fact to put t to infinity in this rational expression by saying that this expression, let's say is t go to infinity, we have the same term there, so this go to -1. So you have several terms in this product. So this will go to this sum. That's the full one. Yes. Like this. Okay.
Sorry, you are implicitly assuming that M is smooth, right?
Yes. The ambient space is smooth, but we choose a resolution for the function. Again, I go maybe a bit fast in this, but I don't need all of that. Just to make sense of what this object is. That's just my goal at this point. Somehow, what appears there will be not relevant for the remaining of the talk, but just to make sense of the objects. Okay, so just I finish there. This is going to -1 to the cardinality of J on times this algebraic variety that I didn't define precisely, but anyway, we'll encounter them later. And what you find here is exactly the Motivic Milnor fiber up to a sign. So this is minus this object that appears in the very introduction. Just to say that this object comes from a natural generating series associated to the function. So this is naturally associated to the function. What is maybe not so clear is what this has to do with the Milnor fiber, but then there are some results for this.
Assuming those Lj right there are not a Bj of zero.
This is a big J, yes.
You wrote L below B.
Where are you? I think there is no L except this one, but my writing is maybe not very good.
So in the bracket there you wrote B?
Here?
No.
Here, this is, yes, some L with subscript capital J.
So it's not the D of B dot.
No, but this is related to this D. We will see it again in a moment.
Ah, it comes from R.
I mean, yes. At least it comes from the zeta function. Oh, yes. Okay, so yes, this is related, again, this is some integers related to the resolution. But as you see, they completely disappear here, so I don't need them later on. Just this exists, yes? Don't worry about the value, this exists. And that just these objects now are of some importance, and of course the signs also. Also, as I mentioned previously, there is some relation between this and the topological Milnor fiber. So let's state this as theorem. So that DNF and other, as I mentioned, that maybe let me specify this. So these objects, when you evaluate them with some additive invariant, then they are the same. And here you can put any additive invariant you know, additive or multiplicative, so Euler characteristic, or Stirling polynomial. And whatever you want. So that's my DNF and loss. I didn't mention monodromy yet, but of course you have monodromy action on this topological Milnor fiber by, say, going around the origin in C that leads to a monodromy, geometric monodromy on the Milnor fiber. And you may also consider this monodromy in the Motivic setting, so I don't want to precise this much, but already Arthur said something about this with some mu hat appearing here. So, this, yes. And so you can take into account monodromy by adding some action everywhere in this story. And then this is also compatible with monodromy. But just for simplicity, let me completely avoid monodromy in this talk. Almost completely, at least. So of course there is some question also why this should be true. So let's say or maybe why should it be true? I mean, there is a proof, yes, but so the proof goes by, yes, computation. I mean, you can compute this object using a resolution of singularities, and you can do the same for the Milnor fiber, for example, using a A'Campo approach, and then you compare your number and they're the same, but you are looking for, I mean, maybe more intrinsic relation between these objects. So there are some other approach to say why this should be true. So let me mention several names there. Approaches by, so let's say Nikes Sebag, Ryszowski, Loza.
There is some V missing. V is missing.
Sorry. Thanks. Where are you for that? There. Ah, okay. And some others. So Arthur discussed about that already. Yes. And so Arthur. I should mention Nikkei Spain also. And maybe Arthur with Yimu also. I don't know if I should put it there. Arthur is where? Arthur is there. Yes. Should I put Yimu there also? Why not? Yeah. Or both of you? Yes. On these approaches, I think all go via non-Archimedean geometry. And somehow in this talk I will try to provide another approach. So maybe we do not give the full of all of this, but at least we make a link between this Motivic and topological Milnor fibration. This was the first question. And the second, again, is this question of signs. So interpretation of the signs. So maybe to finish the second introduction, this was the first introduction, and this is the second one. Let me write down a diagram. We try to give some answer to this question. So I will try to explain the construction of some spaces, say via logarithmic geometry in this talk. So this will be these spaces. So let me denote this like this. MD. Maybe I should mention something somewhere. At least from now. I will assume that my function has already normal crossing. So I have already used a resolution. So let's say that the zero set of f is already a normal crossing device. So just to forget about the resolution, we have already used it. And so in this setting, I will try to explain the construction of some log spaces. So this is the first one with a log. There is a here for, say, algebraic. Maybe I will put here just logs. That will be the log space that Patrick explained in his talks. And inside I will have another one that will be a somewhat complete log space. So there will be some relation between these log space, so inclusion and projection. And these spaces will come with morphism. So here we will go to S1. So this will be a log version of the function f. Here we will go to C star. that you can see some algebraic version of S1. And here we are going somewhere. But this is something like, how to say? Let's say C star union S1 for the moment at least, with some morphism. So my goal is the remaining of the time is to try to explain what is this diagram. On the right-hand side here, that's what Patrick explained. So let's say that Kato-Nakayama approach of the Milnor fibration. So this we already encounter. On the left-hand side, so that will be a log space, I mean constructed via log geometry, but essentially this will be a recollection of all this algebraic variety that appear in this formula for the Motivic Milnor fiber. So this we can, I mean this set at least we can describe as a union of all this L star J for all J there. Probably not empty. And this in the middle is some way to glue together both the Motivic Milnor fibration that will be there and the topological one, which is there. So that's some place where to put everything together. So that's what I will try to explain. Feel free to ask questions if you want. So let me try not to explain the construction of these spaces. So that will be the log point of view. So if, maybe I have to say a word or two about the definition of the log spaces. Even if certainly I will not enter into the details, but so again we have our non-singular algebraic variety there. We have inside a normal crossing divisor, and to this situation we may associate a divisorial log structure. That Patrick mentioned already. So that will be given by a sheaf of monoid. Which will be, so let's call it, oh yes, that's not the same M, but anyway, but sorry. Which is given by its stalks. So you will only consider the non-vanishing, I mean invertible function if x is not in the divisor, and all function if x is outside, is inside, sorry, the divisor. So that's a sheaf of monoids. So monoid is just like a group with no inverse. So you have just multiplication, and also you have existence of identity, I mean neutral element for the law. And so we will use several examples of monoids. So first one we encounter several times is a circle with multiplication. Of course, this is a group, but anyway, it is a monoid too. C star. Maybe again this is a group, but anyway. Let's say strictly positive real numbers will be also a monoid, maybe also a group. And let me give maybe one example of a monoid which is not a group. If you add infinity there, let's say plus infinity for it to be positive. And then you can multiply a positive element with infinity. This gives infinity, but of course infinity doesn't have an inverse. So what are we going to do with that? Well, we are going to construct these log spaces. So let me begin with the construction of the classical Kato-Nakayama space, or the rounding that Patrick mentioned several times. So let me describe it like this. So I will take x phi probably, with x in M, and phi will be a morphism of monoid between the divisorial, the stalk of the divisorial log structure with value in S1, and I add some relation or some condition, sorry, so that for any function in this stalk, but which is an invertible function, then I impose the value of this morphism. This will be the value of j at the point x divided by this modulus. So that's the set construction of this space. So maybe to use the notation of Patrick, that was M with something like this.
Well, the M dagger, so you can put a D below to remember that you
Yes. So as soon as we have this sheet of monoid, this gives M. If it's dagger, we have the structure on.
I think we should correct the second thing, because the stalk at X on D is made of germs of functions which should not vanish outside D. So written like this, the function 0 belongs to that, but it's not allowed in the stalk at the top, because it should not vanish outside it. So it's a different monoid than the multiplicative monoid OS.
Okay. Let me skip it like this just for this. Maybe better to have a bad definition than no definition. I don't know. So.
With another definition of MX, the rest is correct.
Okay. Anyway. So just to give some hint for this, yes. So this condition makes that if your function is invertible, that you have no choice for phi. So it means that if x is a point outside the divisor, this adds nothing to the story. So outside the divisor, you do nothing. This is just m minus the divisor. And the only thing we change is when x is inside the divisor, then you have no longer condition, and somehow you are associated above this point, some point in S1. So maybe to make a drawing, just to summarize this story. So this space is essentially the same thing as M, at least outside the divisor, and inside the divisor, let me put div. So the divisor is no longer there, but you replace it by S1. So above 1 point in the divisor, let's say this is x, you have replaced this point by S1, and you do this along all points in the divisor. On outside, that's just m minus the divisor. So you see this tubular neighborhood that Patrick discussed, but of course there is nothing inside the tubular neighborhood. So the boundary of the tubular neighborhood. So you have replaced m by this boundary of a tubular neighborhood. So that's this space. To define this one, well, it's just the same. So let me put it here. So it will be the same thing, but you just replace S1 by C star, another choice of monoid. And then the condition you add here is just, well, you erase this. So the condition is just that phi of j. Do I need it like this? Yes, I want maybe to say that this is x and capital phi. And this is just g at x. So again, if you have a point which is outside the divisor, you have no choice for your function. But if you are inside the divisor, then you choose some non-zero complex number. So that's just one way to fill the tube with complex numbers. So you see inside your S1, here you have let me draw it like that. That C star. So now you have the tubular neighborhood, but with what is inside. And so that was for the left-hand side. And for the middle part, well, you have just to choose another monoid there. So let me try to write it somewhere. That will be that's a bit more complicated. Essentially, that's not exactly correct what I will say, but essentially we replace this by C star union S1. Okay, time is running. Let me not define completely that, but it's just one way to put together the information about the argument of your number on the value. But I see just 5 minutes left, so I want to say a bit more about these things. Okay. So I mentioned. Okay. So at the level of monoids, so we have some relation between all these things. So C star, of course, you can insert it in C star union S1, and this you can project to S1. Actually, the way we see this object, so that's monoid, but we can see them geometrically. This can be seen as the real-oriented blowing up of a point in a C. Or in another way, let me draw this like that. Let me say that this is C star. On this S1, I will put it at infinity. So look at this as a compactification of C. So you can add the point at the moment, this is of no importance. You compactify C, but not with one point at infinity, like if you are doing the projective space, but you compactify by all the direction of the lines. And so you compactify by one S1. This is exactly the real-oriented blowing up of, say, P1 at infinity. So that's what appears here. Of course, you have this inclusion. of this projection. Of course, you have also an inclusion in the other direction, but that's not a morphism of monoids, because S1 will go to infinity there, and so the neutral element is not there. So you have also inclusion there, but this is not a morphism of monoids. So you have also inclusion of this space inside here, but not as the log space, but as just space, you have it. And by this, this inclusion and projection, you see that you can pass from the first one to the last one, essentially by dividing by, say, the action of real positive numbers. That's what is the definition of the real oriented blowing up who do that. And actually this division here, so you can recover here it on the drawing, yes, you obtain the boundary here by dividing the interior of the boundary by this action. So that's the drawing when you have only one divisor, but when you have several components of your divisor, then you have a fiber product, all these constructions. And so you may have a division by bigger spaces than this one. So that's a quick explanation of these different spaces. And just to finish in 1 minute, so again, you have some way to pass from the left-hand side to the right-hand side by division by some power of real positive number. So the power which appear here actually will depend on the strata you have there. If you have only one divisor, it's just one power of R, like in my drawing. But if the set J has more than one element, then you may divide by several elements here. And this gives you some hint for the discussion about the signs. So let me finish with that. So if you are, so we have this, let's say alog. So that's the algebraic one. You can restrict it above, let's say, one of the strata which appear in the resolution or in your divisor. And above such strata, when you pass from this set to the logarithmic one, by dividing by the adequate power of positive numbers. Then these go to C star. Here also you pass by dividing by real positive number. So if you cut this space into stratification, I mean the natural stratification related to that, you know to pass from one set to them. So of course this one is algebraic, this one is topological, so if we want to compare invariant, it's a bit difficult. But a bit as additive invariant, you can consider that the additive invariant related to such a set, which is of course not a complex algebraic set, but you can say that it's earlier characteristic, which is -1. So at least topologically, you divide by, say, -1 to the power j to pass from this set to this set. So this gives an hint for the -1 to the j appearing in this sum. So in the definition of the Motivic Milnor fiber, but of course, yes, this is there maybe. And of course, you have one more minus sign, which is here. And this additional comes from this division. Again, heuristically. What I am saying here is not a mathematical proof, it's just some heuristics, some way to try to explain how we can relate the topological Milnor fiber on the Motivic one. So Motivic creates this space. And we have some here topological way to pass from one to another. Okay, let me finish here, and thanks for your attention.
Thank you. So thank thank you very much for this interesting talk. Do you have some questions, comments?
Can you maybe say a word about the C-log?
Yes, I can even give the definition if you want, but as mentioned Patrick, I mean, the definition, you are going to take triple here. Let me write like this. X, phi, and the third one, let's say like this, where maybe psi. The first one will be in the log space. And just the last one will be like this, but you are going to 0 plus infinity by considering the modulus here, or maybe the inverse of the modulus. So that's just some way to put together inside or outside. So of course, when you have only one component, this is just a union of both sets. But as soon as you have several components, two components, then this over space is more than the union of this one. You have some part to add. And this is very important if you want to deal with monodromy, but I didn't talk about monodromy. You know, that's some more A'Campo model from the Motivic Milnor, for the topological Milnor fibration. And A'Campo, if you want to consider just the fiber, this model is perfect. But if you want to consider the monodromy, he has to do more work. He has to give some more freedom for the different monodromy along each strata to glue together. So he has a procedure by adding simplices to make a bigger space to construct monodromy. And somehow exactly this space allows to do this. A similar space appears in Kauberg's work, in Kauberg's thesis. So it's not exactly the same, but it's very similar to that, exactly for this question of monodromy.
Okay, some more questions? No, if not, so let's thank you.